This is another popular misconception. Currently, this is the trending topic in physics. Khan sir has made some remark, and Pankaj sir has corrected it, and there is a controversy going on between both these teachers. So I also thought of clarifying this point. So these are some of the misconceptions which generally students have. So resistance opposes current. So many times what students think resistance opposes current means, they think if this is a resistor, then if current here is 6 ampere, if 6 ampere current enters here, then they think maybe some current which is less than 6 ampere will come out, because resistor or resistance, it opposes current. They think if 6 ampere enters here and 4 ampere comes from here. It's not like that. Resistance opposes current does not mean higher amount of current is entering through the resistor and a lower value of current is coming out. This is incorrect. Then what is the meaning of resistance opposes current? So resistance opposes current means, let's say you have a battery. Let's say you have a battery, for example 10 volt. Now here if you connect it to a resistor, 2 ohm resistance, then the current comes out to be 10 by 2, that is 5 ampere. But here if you connect it with a higher resistance, let's say 3 ohm, then the current comes out to be 10 by 3, that is 3.33 ampere. If you connect it to a resistor, let's say 5 ohm, then the current comes out to be 10 by 5, that is 2 ampere. So if your resistance is 2 ohm here, so here we are connecting all the resistors to the same battery, and then we are comparing. So if your resistance is 2 ohm, it's a lesser value of resistance you are connecting here, you are getting a higher value of current. If your resistance is 3 ohm, your resistance is little bit higher, then you are getting a lesser value of current. And if your resistance is higher, 5 ohm, then you are getting still lesser value of current. So higher the value of resistor in the circuit, lower the value of current you get in the circuit. That's the meaning of resistance opposes current. And in all these cases, the same current enters through the resistor and the same current comes out. Like when resistance is 2 ohm, so the current flowing through the circuit is, so when the resistance is 2 ohm, the current flowing through the circuit is 5 ampere. That means 5 ampere current enters here, 5 ampere current only goes out here. It's not that 5 ampere current enters and a value less than 5 comes out from here. No, the 5 ampere current keeps on flowing in this circuit. But if the resistance has a higher value, 3 ohm, then the current is lesser, 3.33 ampere. So if the resistance is 3 ohm, then 3.33 ampere current keeps on flowing. 3.33 ampere current enters here, 3.33 ampere current goes out from here. If the resistance is even higher, let's say 5 ohm, then the current is 2 ampere. That means higher the value of resistance you take in the circuit, you will get the lower value of current. In that sense, resistance opposes current. But whenever a resistor is connected, same amount of current enters and comes out of the resistor. It does not mean higher value of current entering to resistor and a lower value of current coming out. This is another popular misconception, how current flows in a circuit. So generally students think that when you switch it on, the electron starts from battery and then reaches the bulb and then comes out again to the battery, and it takes some time for the current to get established. It is not like that. It's not that when you switch it on, then the electron starts from here, goes to the bulb and comes out like that. No. Whether you switch it on or off, electrons are at every place. Electrons are at every place. And they are not at rest. Even when the switch is not on, the electrons are not at rest. They are moving randomly in all directions. That's called as random velocity, and the average velocity is 0. That means although this electron will be moving like this, but over a period of time it will be there only. Although this electron will be moving randomly like this, and they move with very high speed, 10 to the power 5 meter per second, but over a period of time it will be there only, right? But when you switch it on, then in addition to those random velocity, now the electrons start drifting That means here, when you switch it on, current has to flow like this. That means the electrons has to flow like this. So the electrons flow like this. So as soon as you switch it on, it is not that the electron starts from here and reaches here. This electron moves here, 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 this electron moves here. That means all the electrons, wherever they are standing, as soon as you switch it on, they start moving like this, in addition to their random velocity. This is how the current gets established. So it doesn't take, whether the wire is short or long, it's not going to take different amount of time. It's not that the electron will start from here and has to reach the bulb, then the bulb lights up. No, all the electrons, wherever they are, as soon as you switch it on, they start moving like this. And as soon as you switch it off, wherever the electrons are, they stay there. So the popular misconception is that students think that if the switch is off, then they think current is coming up to this much. Current is coming up to this much, and it is not able to pass through this much. That is a wrong idea. So I thought of giving a proper analogy, and I came up with this traffic signal. So how do we think and how exactly it is? Let's say here is a road. Let's say here is a road, and here is the traffic signal. And here is the traffic signal. Now, how students think, when the traffic signal is red, then they think that, some people are waiting here and some people are coming, some people are coming, some people are coming. And here the crowd is going on increasing. This is what happens when you switch off the switch. This is what students think, that there is a traffic signal. When it is red, so no one is going from here because there is no one here. But here people are coming and gathering. So दिमाग में यही आ जाता है. They think when the switch is off, as if यहाँ कोई इलेक्ट्रॉन फ्लो नहीं हो रहा है, लेकिन यहाँ तो फ्लो हो रहा है, यहीं तक आके सब गैदर हो रहा है, धक्का मुक्की चल रहा है यहाँ पे. It is as if like that. No, it's not like that. So I am giving you another example of another traffic signal. So consider it like this. This is a traffic signal. When it is green, all are going. When it is red, everyone stops. The people here as well as the people here. When again it is green, let's say all are moving. When it is red, everyone stops wherever they are. If you think such a kind of traffic signal, then you will be able to understand the current flow here. So when it is switched on, all the electrons, wherever they are, they start moving. And when you switch it off, wherever they are, they stop. It's not that electron from here starts and comes here, and if the switch is not open, then they start gathering there. So as if electrons are coming here and they are colliding and pushing the switch. So electrons are coming here, they are just not able to go here, and there is the electric meter here. So even if the switch is off and there is no current here, because electrons are able to come up to this much, current is able to flow here, so the meter reading will increase. It's not like that. When the switch is off, everywhere the drift velocity of the electrons has become 0. They only have random velocity, which doesn't contribute to the current. Hope I am clear.